So have you said? So let me know when we're set to go. The stream is on, okay. And the audio? Just check the audio and then we'll start, right? Okay, good. So morning, everyone. We're going to pick up where we left off in the last class. This was supposed to be the last class. And of course, all of you are, I'm assuming all of you have at least made one attempt at submitting something for the homework. Right. So this is a time-honored tradition among students. When we tell you that, it's a 12 hours a week course, then you assume that, you can pack those 12 hours times 4 into 48 hours and finish all of your homeworks in one day, which will magically stretch to 48 hours just before the deadline. It doesn't work that way. We have a saying in India, you can't have a baby in one month by making 9 women pregnant. So this is pretty much what you guys are trying to do. It's the homeworks should ideally have been sort of worked on in increments, and we should have resolved at the least AWS issues and such like by now, know how to get things running, make sure that your code's kind of running, that you don't have bugs. We've had plenty of time, right? Now finding at the last minute that your code is a bug and your classifier is producing the same output for all classes really means you're kind of late on the scene. So let's not do this for homework 2. One of the things is homework 1 was 3 weeks long because we gave you the extra time which you very smartly used by not working on the homework for 2.5 of those weeks for the most part, because we expected you to use this extra time to get familiar with the infrastructure, how to get on Amazon, how are we going to get things running over there. And then, of course, there's this whole business of optimization, training neural networks and coming up with reasonable results is not as a non-trivial thing. You can't just run, grab the code, run stuff, and have things work. If it were that easy, things would be nice, right? So it's not hard, but it's definitely about 2 or 3 weeks of work to get it running the first time around. Once you get the hang of it, subsequently it's not so hard. Afterwards, it's tedium rather than, terror, right? So that was the point of this first homework. Get everything set up so you can actually do subsequent homeworks, your projects, whatever, and be comfortable dealing with neural networks. So anyway, we're kind of hoping that all of you will get things done, if not, by today, before your grace days are up. Let's see. All right. So I'm going to continue with where I stopped off. For a quick recap, the last thing we spoke of was incremental updates, training. Now, your standard batch update looks at the error at several training instances. So you might have many of these training instances, like these 5 lines over here. And there's an ideal function shown by the dotted line. And the idea is to somehow grab the function at all of these training points and adjust them all at once and try to make it fit the target function. So you might start off with an initial guess, and then at each of those points, some of those places you want to pull the function up, some of the places you want to push it down. You want to do all of this simultaneously, one step at a time, slowly adjust the function till it looks like what you want it to look like, at least at the training instances. The problem is that for something like this, you would have to process all of your training instances before you made your first update. You have to know that at these 3 locations it must go up, at these 2 locations it must go down, and then sort of come up with a global fix that tries to do all of them at the same time. And this can be really slow, right? So we saw that the alternative was to pick each point and make little adjustments at every point. And if you cycle through this properly, hopefully at the end of it all, you would still get the same outcome. And you know, if you cooked in a kitchen and tried to make bread, you know, you can shape things, and you don't try to shape all of it at once. You shape it in pieces, right? So this is how it works. Now, so the overall algorithm would look something like this. You'd be going over all of your training instances, but for each training instance, you'd compute the derivative with respect to every parameter. Yes?
Which slide deck is this again? Is it the or lecture 8? So it didn't seem to match the one on the screen. Yeah, I think we don't sync properly.
So lecture 6, okay. So I have, give me a second. This one is lecture 6, stochastic gradient.pptx. Get it? And the first 6 slides shouldn't have changed anyway, right? They're the same from. It starts at slide 45 or so. Right? Anyway, nothing lost because this is just old hat, right? Look at the slide number. This is slide 50. Right? Good. Okay. So for those of you who didn't quite see the slides, you can just go back and look over the slides and match the audio to what's on the slides. We just sort of quickly recapped what we ended with in the last class, or the class before last. The last class, of course, was cut. So the point is, if you do this one point at a time, eventually you expect that if you're careful enough, you're going to match the function, right? Now, and even if you do it one point at a time, eventually you're going to be touching all of your training points. But then in the process of touching all of your training points, since you're updating after every training instance, you're going to have, hopefully, a greater overall correction than if you just performed one batch update. So a caveat that we mentioned was that if you, slide 54, right, you'd have to make sure that you go through the samples in random order, because if you went through them in the same order every time, then if you loop through the samples in the same order, you may just get cyclic behavior. So you start from the left, and then as you go through the samples left to right, the whole thing swings up like that, right? It swings up like that when you get through the first batch of points, and then swings back like this when you get through the second batch of points, and repeats, right? So this kind of cyclic behavior might be expected, so you want to be picking samples at random. Now, here's an explanation that's sometimes given, which I'm not terribly fond of, but it might give you the intuition. So let's look at an extreme example. When we perform gradient descent, batch gradient descent, what we are really doing is computing the derivative that's given on top with respect to each parameter, which is the average of the derivatives of the divergences for the individual training instances with respect to the same parameter. Now, if you're currently at this point, that black point, the derivative with respect to any individual instance could be pointing in any direction. So all of those blue lines might represent the derivatives with respect to the of the errors for individual training instances. And what we will do is take the average over all of those shown by the red line and then walk in that direction. But now, let me give you this extreme case where all of my training instances are identical. They're all the same. So through some, misfortune, you manage to select 50 training instances all alike, or 50,000 training instances all identical. Then what happens? The average gradient is no different from the gradient for a single training instance, right? So what will happen over here? If I perform batch update, I'm going to be going over all T training instances to get the same result that I would have got if I'd only looked at one of them. And so if I updated my parameters after each training instance in a single pass over the training data, I would actually end up with T updates. as opposed to a batch update where I'd be processing all t instances and just get the same outcome as if I'd updated my parameters after seeing just one training instance. And this is because all of them are alike, right? All of them are identical. And they don't necessarily have to be identical. They could be really close together, in which case the same kind of behavior might be kind of expected, right? And as the data get increasingly diverse, you would expect that the benefits of incremental updates are going to kind of decrease, but they don't entirely vanish. This is a reasonable expectation, right? This is just meant to give you the intuition, but let's go back and look at the storyline that we had last week. So now, as we are performing our incremental updates, the first criterion, of course, is that we must be picking the instances that we will update in random order, and this order must change from pass through pass. But then, except in the case where your network finds a perfect fit through all of your training instances, the function that the network captures is going to be imperfect for every single training instance, because you're finding some kind of an average. So if you're always correcting for the last training instance, your update is going to be unstable. So we figured that what you really want to do is decrease the learning rate as training progresses, so that the amount of adjustment you make in response to the latest training instance decreases, and the entire process can converge. So specifically, we found that the conditions, so let's keep up with the slide 72, right? Conditions we needed was that we wanted the absolute, remember that our learning rates are all positive, right? So we want the learning rates to not be absolutely summable, but we wanted them to be square summable. What was the point of them not being absolutely summable? This was a question that came up on Piazza. So let's say that the derivative of the gradient with respect to let's say the derivative of the divergence with respect to any parameter is, for any x, right, is upper bounded by some d. Then what happens? The updates that I'm going to make, the total update over infinite time steps is going to be t equals 0 to infinity eta t, right, d divergence of x with respect to xt, right, w, where xt is the tth instance that I'm considering, which is going to be less than or equal to d times summation t equals 0 to infinity eta t. So what does this mean? If this summation term over here is finite, then there's an upper bound on how far away from the starting point I can go. Because I'm never, so let's say this term, the summation is some value c, then the net correction is never going to be greater than d times c, right? Which means if I start off from the wrong point, there's a boundary I can draw beyond which I'm not going to be able to search. And if the optimal value lies outside that boundary, I will never really reach it. So as a result, you want the steps to not be absolutely summable. You want to be able to explore the entire space. At the same time, as you go through the data, eventually you want the steps to get smaller and smaller and smaller, and so you want them to be square summable. And we found that an optimal step size for something of this kind was 1 over k, right, or a good step size. Now, when Tom went through his lecture, he would have actually talked about the schedules you use to decrease learning rate. So all of them sort of conform to this criterion. Now, we can speak of convergence. How fast does the algorithm converge to a solution? And traditional, there are different ways of defining convergence. And the standard one standard way of defining it is a so-called epsilon convergence. How many steps must I take? How many iterations must I run before the current estimate is within current estimate of the function is within epsilon of the optimal value? And we find that for strongly convex functions, if you're actually using stochastic gradient descent, which is updating after every single instance, you're going to take of the order of 1 over epsilon iterations. to get to within epsilon of the optimal solution. Or if the function is not strongly convex but just convex, then it's going the convergence rate is 1 over square root of k, which basically tells me that if the distance between the wk minus w star is going to be less than or equal to 1 over square root of k w0 minus w star. So basically, you're going to be converging at a rate which is square root of k, right? So you want this multiplicative term to be as small as possible, because the smaller it is, the faster you're converging. And stochastic gradient descent is going to be converging for our generic convex function at the rate of 1 over square root of k. Did I just?
We're all good. We switch back to the other camera.
Okay, I'm sorry. Oh, yeah, okay. So now, when it comes to batch gradient descent, batch descent actually has a much nicer property for strongly convex functions. It actually falls off as c raised to k. So as you can see, batch convergence converges to the optimal value much faster than stochastic gradient descent. But then the point is, when you're performing batch updates, you're going to be processing t instances for each update, whereas stochastic gradient is going to perform t independent updates in a single pass through the data. So because you're performing a greater number of updates using stochastic gradient descent, in the net you might actually converge to the solution faster than if you're just using batch. But then you have these other issues, which we saw in this little example, that the variation across the final outcomes that you get is going to be larger for stochastic gradient than for batch updates. Yes?
Question from the stream. In reality, are we using exponential decay?
So we are not using exponential decay. This is just if the function were strongly convex, it would be decaying exponentially. Our functions are not strongly convex. But we're speaking of a best case over here. But in every case, you can show that batch gradient is going to converge faster than stochastic gradient in terms of the, for any given number of steps. But SGD has a greater number of steps. Right. So here was the other issue that we saw, that if you actually looked at the solution that you arrive at, then across different runs, the variation is much greater for stochastic gradient than it is for batch updates. And secondly, of course, the function value that SGD converges to in this example is significantly worse than the function value that batch converge to. Now, this is not always going to be true. We can cook up examples where SGD will find the correct answer, whereas batch update will not. But the fact that the variation is greater for SGD across different runs will always hold. So what do I mean by this? Now, let's say I run an experiment. Now, in the experiment, I'm going to be gathering some training data I'm going to be collecting some training data, and then I use that training data to estimate my parameters. Each time I run an experiment, I will start with a different set of training data, right? So here, these are all the results I get in different experiments where I use different training data. And you can see that depending on the training data, I will get different answers, and the variation is greater for SGD than it is for batch gradient. And in reality, we don't want such variation. So why do we actually get such variation? We saw the reason for that too. And the reason was this, that what we are really trying to optimize is the expected divergence between the output of the network and the actual output that you desire, actual output of the network, and the output that you desire from the network. So for every single input x, for any given value, any given parameter w, the network will have some output, and there's some desired output, and you can compute a divergence between the two. This divergence is a function now of x, and the expected value, ideally this divergence is going to be 0. Now, we can't really compute the actual expected value because you're going to need the need to integrate over your entire training space. You need to know the function. Instead, we compute an empirical estimate of the expected divergence. And the way we do it, we average the divergence across many training samples, and we get an average divergence. And we can see that the expected value of the average divergence is simply going to be the expected value of the divergence itself. This is just a property of random variables, right? The expected value of the average of many draws of a random variable is exactly the same as the expected value of the random variable itself. But then here's the second factor. So the empirical error is an unbiased estimate of the expected error, which is great. Or the empirical loss is an unbiased estimate of the expected divergence, which is great, right? So this means that I can minimize this and hope to minimize the expected value of the divergence, because one is is an unbiased estimator of the other. But then, it's not that clean, right? The problem is that what we are really doing is averaging over many samples. And when you average over many samples, you have the standard property of random variables. You have, so first, for any y equals ax, the variance of y is going to be a squared times the variance of x, right? This is just a standard property. Secondly, if I have y equals summation I xi, I equals 1 to n, then implies the variance of y equals summation I variance of xi. This again, so long as the xi's are independent. So this too is a standard property, right? So combining those two, if I look at this, I'm going to find that the variance of the error equals 1 over n squared summation I variance of divergence, which is going to be simply the variance I equals 1 to n, where n is the number of training instances, variance of the divergence over n. So the larger the number of training samples, the lower the variance in the estimate of the expected divergence that you will get, right? So when I perform stochastic gradient descent, when I'm performing batch gradient, this is the guy that I'm trying to minimize. And if n is large enough, meaning if I'm drawing a large enough number of training samples across different runs, I expect to see more or less the same loss function. And so I expect to converge to the same point. On the other hand, if I'm performing stochastic gradient descent, for each individual training instance, remember I'm performing an update after just seeing just one training instance, right? So for each individual training instance, firstly, the divergence, the expected value of the loss is still the expected value of divergence. So this remains an unbiased estimate of the expected error. But the variance is going to be the variance of the divergence itself. So which means okay. We also saw a pictorial example of what this means. Now let's say the blue curve is the curve that I want to estimate. My current estimate of the function of the curve is the red curve. This is the output of my function, of my network as a function of the input. So the shaded area is the total error that I'm making. And I want to adjust the parameters of the network so that such that the shaded area decreases. Now, to compute the shaded area, I'm going to have to see the value of the function, the value of the output of the network for all x. And clearly, we're not going to be able to see that. Instead, we compute the output of the network at a small number of samples. And we can compute the error at each of those samples, which are those little blue and red lines. And we are taking the average length of those little lines as some kind of a quantification of the shaded area itself. And that's what we are trying to decrease. But then, depending on where you choose those samples, the average length that you get is going to be different, which means that our estimate for the shaded area is going to change based on the training samples that you actually choose. Which is why if you change your training samples, you're going to end up with a different the different estimate for the network itself. Now, one way to combat this is to have just a very large number of training samples. The more the number of training samples, the less the variation between experiments in the estimate of this shaded area, and so the more consistent your final network is going to be. In the case of stochastic gradient descent, for any single update you have only one point. So depending on where that point arrives at, and you're going to see a completely different estimate of the shaded area, and you're going to make a completely different correction to the network, which is why you have this large variance between the output of the between the networks that you learn from different training instances. Somebody had this question in the last class, so I'm just going over this again, right? So here we have this these contradictions. SGD uses the gradient from only one sample, so it has very high variance. On the other hand, it provides quicker updates because in a single pass through the data, you're going to be updating after every instance. So you'd like to strike some sort of a balance between the two, right? And clearly, the fact that there's a high variance is not a problem if all of your training instances are identical. So it depends also on the training data that you've actually drawn. So we'd like to have some kind of a medium between the two, where on one hand you have many updates but potentially high variance, and on the other hand you have potentially much lower variance, but it's much slower. So, and the way you can do that is by drawing multiple samples at the same time. So instead of trying to use all of your training samples, in each update you're going to draw some subset of your training samples, like this one. And so at each update you're going to adjust the function at a small randomly chosen subset of training points. Now, what is the criterion for this randomly chosen subset of training points? Intuitively, we say that if I have a very large collection of training data, if I randomly choose some subset from this training data, this random subset is representative of the larger set. And so I can make a correction based on this random subset. But then to make sure that this works, you want this random subset to be truly randomly drawn. So you want a uniform distribution over the actual training samples. And you want this, this again came up repeatedly in on Piazza, right? And you want the samples that are drawn to change from iteration to iteration. So one way to do this is to randomly permute all your training samples and then go through it B samples at a time and make an update after every B samples. This B was what we called our mini batch. There was a mini batch size, but the rest of the criteria still remained. You still had to have the learning rate converge, because if it didn't, then you're going to always be chasing the latest mini batch, right? So again, why would this be better? The mini batch error is the average of the divergences over the training samples within the mini batch. And the variance of this again is an unbiased estimate of the expected error, but the variance is 1 over b times the variance of the divergence. So this is actually much smaller. Remember that as b increases, 1 over b falls off rather sharply. So in the case of stochastic gradient, the variance and the loss function that you're minimizing is exactly the variance of the divergence itself. Here it's 1 over b times that, right? So which means that as your batch size increases, even for small increases in batch size, you can actually see a significant reduction in the variance of the loss function. Yes?
This might be a silly question, but is there an advantage to having essentially overlapping batches, right? Because if you take mini batches, you're effectively putting a rectangular window on the training samples,
It's,
right?
well, depending on how you visualize it. Okay.
Right. But then you have non-overlapping mini batches. Is there something to be gained by overlapping?
So the way I've written it, I had non-overlapping mini batches because it's the most effective way of passing through your training data.
Sure.
But if you want to be truly random, you want to be drawing with replacement, in which case you will actually have, overlap. You may have overlapping boxes. But implementation-wise, it's easier to just sort and go through it, and if your data are large enough, it's going to have the same effect.
Is the bigger mini batch the better the
So again, this has to do really with this term over here, amongst other things. We will see there are two different effects. The first, of course, is the variance of the loss function itself. So beyond a point, whether you have a batch of 1,000 or a batch of 10,000, the variance is going to be pretty tiny, right? So at which point you're really not gaining very much. On the other hand, you're putting in a lot more computation. So you don't want your mini batch sizes to be too large. As far as the variance is concerned, you're losing the benefits of multiple. You're not gaining anything in terms of variance. You're losing the benefit of being able to perform multiple updates as you go through the training data. But then there's a second aspect to it, which is this guy, which has to do with convergence rate. So for convex functions, for stochastic gradient, the convergence rate is 1 over square root of k, which is what we had over here, which said, I've erased it. How much closer are you to the optimal value when compared to your initial estimate after k iterations? That decreases as 1 over square root of k for stochastic gradient descent. For mini batch gradient descent, that decreases as 1 over square root of b times k, right? So as b gets larger, you expect to get to the solution faster and faster and faster. But here is the trade-off. For a single mini batch of size b, you're actually performing b computations. Whereas for stochastic gradient, you're only performing one computation. So in effect, you're actually doing b divided by square root of b times k. So in principle, this is going to be dominated over by you're going to have an increase in computation of square root of b, unless the whole thing is dominated by 1 over k. Where you actually gain is, so you have these two different things going on. Remember, convergence is independent of variance. Convergence is what you will get for a given training set. Variance is the variation across different experiments. The training set itself changes, so you have the trade-off. And the sweet spot tends to be a bit heuristic. In practice, what we will find even in terms of convergence is that although this is supposed to be slower, you can perform vector operations, use parallel processing, and so on. So even for convergence, mini batches are going to be much more effective. Again, I don't have a golden answer for what the optimal mini batch size must be. Many of these things are eventually empirically derived. But then here is the behavior that you expect to see. This is again for the k-means example that I had earlier. Observe that stochastic gradient doesn't quite converge to the correct thing. Batch gradient converges to the correct thing, but after a lot of time, mini batches converge to essentially the same answer as batch gradient, but orders of magnitude faster. And the variance over here is not significantly different from the variance over here. So the mini batch descent actually tends to give you the sweet spot between pure stochastic gradient and batch descent. So now I've drawn these plots, right? What exactly are these plots? You generally define convergence in terms of the overall training error, but clearly you're not going to be making an update and then passing your entire training data through the network to converge to compute your error. So we have different ways of estimating the error itself, like class set divergence or classification error on the held out set, or batch error averaged over the past several mini batches. Just being able to come up with a reasonable estimate for what your current loss is, expected loss is a heuristic by itself that can change, right? So for updating your parameters. Now in the case of batch updates, it was obvious that this made sense. In the case of mini batches, this actually has a greater effect, because in the case of mini batches, the gradients can oscillate quite widely from one training instance to the other. And something like momentum smooths that effect out and gives you a lot more stability in the learning process. Same thing with Nestrov's algorithm. In the case of mini batches, you expect to see a greater benefit from Nestrov's method than in the case of batches, simple batches, right? And now, so we see that these trend-based algorithms have this property of smoothing out oscillations in bad directions, sort of enhancing the steps in the correct directions somehow. This basic principle is what motivated both momentum and Nesterov, and this has actually been built upon. And we have several new algorithms like RMS prop, Adam, Adagrad, Adadelta. I'm calling them new because they're new in the bigger sense of the word. The momentum and Nesterov's methods were around 20 years ago. These are for the past 5 years or so. Now, how exactly are these guys different from the momentum method? Why are these considered advances? Let's take a look at this again, right? Here was the typical example that we saw. If you were to use gradient descent, you'd be oscillating and sort of heading towards the optimum. Now, here we see the total movement you see over here in the vertical direction is much greater than the total movement in the horizontal direction. But the movement that you're really interested in is the movement in the horizontal direction, not the oscillation in the vertical direction. And so the momentum methods tried to handle this by using a running estimate, where the running estimate said that, just because I'm using a running average, I will sort of dampen out the oscillation in the vertical direction. I will enhance the steps in the horizontal direction. But then there's a second parameter that also can be used to control this behavior, and that is a parameter that's an integral part of gradient descent itself, which is the step size, right? You can actually you can dampen the step size in directions of high motion. And we can do this by considering some quantification of motion. So how would you know that you have a direction of high motion? One easy way to look at it is to just look at the RMS value of the step size in that direction. If you're moving a lot, you expect the RMS value to be large. If you're moving smoothly, you expect the RMS value to be smaller, right? So if you look at the net step size in the horizontal direction over here, the net distance traveled in the horizontal direction is much greater than the net direction traveled in the vertical direction. But the distance traveled in the vertical direction was irrelevant to the answer, right? So let's actually try to formalize this. Here, in the recent past, the total movement in the y component is high, of the updates is high. The movement in the x direction is lower. So you modify the usual gradient-based update to scale down the step size in the y component, scale up the step size in the x component according to their variation, not just the average. So what was momentum doing? Momentum was only considering the average value of the gradient. But now we are taking an extra parameter. We are taking a second order term, and we're also going to consider the variance. And when you do, all of the algorithms that we saw, Adam, Adagrad, Adadelta, RMS prop, they all sort of codify this basic principle. So here is a very simple example, algorithm to explain RMS prop. All of them follow the same basic idea. So I'm using RMS prop as an example because it's rather easy to explain. Let's say I compute the derivative of the divergences. So let's say, just for notation, this notation over here is the sum of the derivative of the divergence with respect to any parameter, right? Okay. So the squared derivative, this is not the second derivative, this is the square of the derivative I'm representing as dou squared w, okay? The mean squared derivative is going to be the expected value of the squared term. And what we want to do is modify the update rule. At each point, at each step, we're going to shrink the step size by the root mean squared value of the derivative. So what happens? In directions where the step size is quite large, this root mean squared value is expected to be high. So you're going to be shrinking the step size. In directions where the step size is very small, the root mean squared value is going to be larger. So you will either decrease the step size less or maybe even increase the step size, right? So, but then of course, you need an estimate of this root mean squared value in the first place. And the estimate of the root mean squared value itself is obtained using a running estimator. So, because every one of these varies, especially if you're using something like stochastic gradient descent or batch, mini batch, depending on the current training instances being considered, these things can swing around quite a lot. So you will have the estimate for the some squared value, the average squared value, is obtained as a running average of the average squared value at the previous estimate plus the squared derivative at the current step. And this is what you sort of plug in to the formula. But again, the formula, you can look these formulae up in the slides, but you get the idea over here. What is happening is that if you keep track of the root mean squared value of the step sizes, in the directions where you have a lot of oscillation, this root mean squared value is expected to be large. In other directions, it's expected to be small, so you would scale by the inverse of the RMS value to be able to dampen out the oscillations properly. And observe something interesting. This looks a whole lot like rprop, because here's the derivative, here is the RMS value of the derivative. In terms of dimensions, I'm basically canceling out the magnitude of the derivative itself. All I'm retaining is the direction, right? So it's for this reason that Hinton likes to call this an extension of rprop, a more natural extension of rprop. This is just the algorithm, how you would implement it. So I pull these animations out from this website, Denis Yornet. If you go to Sebastian Ruder's webpage, he also has the same figures. So this is a classic function called Beal's function. Here is the optimum. And they show how different algorithms converge to the optimum value when they start from the same training point. So SGD is stochastic gradient descent. The momentum, of course, we know. NAG is Nesterov's accelerated gradient. Add a grad, add a delta, RMS prop. And you will see that stochastic gradient descent is by far the slowest of the lot. And the rest of them are more or less the same, right? At which, for the rest of them, it's just a game. So here's a different one. And the add a delta algorithms seem to go down faster, but again, you can see that the SGD is the one that's really slow. And the interesting thing is some of them actually manage to catch this trend really quickly, depending on the specific choice of algorithm. Some of them are going to spend a lot more time exploring these directions, and whereas others actually find the correct direction to travel in and arrive there pretty quickly, right? So these are nice functions. Here's one with a saddle, and once again, you see similar behaviors. What the only take-home lesson over here is that the actual choice of optimization algorithm seems to be somewhat irrelevant. Other than that, stochastic gradient descent is not a good choice. It's really not a good choice, right? So here's the story so far. Gradient descent can be sped up by incremental updates. The convergence is guaranteed under most points, conditions. The stochastic SGD updates after each observation can sometimes be faster than batch learning. And it's possible to cook up examples where SGD will give you the correct answer, whereas batch learning will not. Mini batch updates after batches, this can be more efficient than SGD as we saw, right? And convergence can be improved using smooth updates like RMS prop. Now the other thing that I'm not mentioning is that there are two aspects to it. One is the convergence rate, the other is the variance. These are orthogonal aspects. So not only do they have differences in convergence properties, they also have differences in variance properties. The variance properties depends only on the batch size. The convergence properties depend on the algorithm itself, right? Okay, so this sort of went through most of the basic ideas. For the rest of the class, we'll go through some tricks of the trade. First, you want to make the network converge better, we can do a bunch of different things. First, we can begin by considering the divergence function itself that we will use, and other tricks which sort of make the training arrive at an optimal solution, a better optimum, or at an optimum solution faster. But first, let's consider the divergence. Now, the divergence function, the loss that we are minimizing is the average divergence over training samples, right? So the convergence of gradient descent depends on the divergence itself, the function that we are trying to minimize. You can define the divergence in different ways. So here, for example, I have 3 different divergence functions, randomly drawn. Of these 3, which one would you really want to use? The guy to the extreme left is obviously not a very good divergence, right? But of the two to the right, which one do you think makes more sense? The one to the rightmost, for an obvious reason. What will happen is that the one to the left, initially everything is flat, you're going to be taking small step sizes. Then when you arrive at the minute optimum, you begin taking giant step sizes which can make you oscillate. Whereas for the one to the right, the behavior is exactly the kind of behavior that you want. So we have several divergence functions that have been proposed in the literature. You've encountered some of these in your homework. The most common ones are the L2 divergence. We all know what this is, right? Just the squared Euclidean distance between the target and the output of the network. You have the Kullback-Leibler divergence, which is, again, what we use, which is the cross entropy, negative log likelihood. All of them are effectively the same divergence function to within an additive constant. And in the case of classification, the desired output is represented as a one-hot vector. This again came up in Piazza. The actual output of the network is going to be a probability distribution, and we'll be looking at the divergence between these two, right? Now, the two most popular ones are L2 and KL. Again, this came up on Piazza, so it's worth looking at it. L2 is particularly favored for regression problems. On the other hand, if you're looking at classification problems, the Kullback-Leibler divergence is somewhat favored, right? And here are some plots. So this is an example where I have just a single perceptron as a function of weights. So this is a network this is a single perceptron operating on a two-dimensional input just for the purpose of illustration. So I have only two weights that I can optimize. The bias is 0 by design, and so I can take a whole lot of training samples and compute the average divergence. This is a function of this is a plot of the average divergence as a function of the weights itself. The figure to the left is the L2 divergence. The figure to the right is the Kullback-Leibler divergence. Now, what is the first thing we observe? Which are both convex? The one to the left is not convex, right? I can actually see the shape. That's clearly not convex. So the L2 divergence in this case is not convex. And someone mentioned that Andrew Ng mentions this on the Coursera website. He has a plot for you to confirm this. On the other hand, for a perceptron, the Kullback-Leibler divergence is convex. It's a nice little bowl. But as far as the optimum is concerned, which of these two would you use? Remember, I said I don't like these plots. I don't like the one to the left. I like the one to the right, right? Now compare this to what we have over here. Which one would you use? You would use the KL because it's got a nice bowl shape. The L2 is not a very nice structure. On the other hand, both of them have a unique minimum. And although the L2 divergence is not convex, if you started off with gradient descent, you're guaranteed to get to this unique turning point, right? So convergence is not a necessary property to have a unique minimum or good behavior. Convexity. It's just a desirable property, okay? So in this case, for classification problems, obviously cross entropy is the divergence of choice. Now, here's another problem. Once we get into dealing with mini batches, one of the primary rationale I actually provided for using mini batches is that we thought that a mini batch has effectively the same statistical properties as the entire training data itself. So this is the kind of behavior you expect. If you see each patch of a different color as a mini batch, your expectation is that all of these patches would lie at the same point, more or less. They may have different shapes, they may have different spread, but they lie in more or less the same area. So I can use any of these mini batches, minimize the error over those batches, and expect to see an improvement in the overall function. Now, what will really happen in the real world is that the batches are not going to all lie in the same point. No matter how you draw them, no matter how careful you are, they're going to have a behavior where there is a covariate shift. Each batch is going to lie in a slightly different region of the space. In fact, they can lie in very largely different regions of the space. So what this means is that optimizing something over here is entirely different from optimizing something in this region, which in turn is entirely different from optimizing something there, which is different from optimizing something on the yellow patch, right? So this is a problem, and what we would like to do is to sort of normalize out this covariate shift. This is the technique that you've encountered as batch normalization. So you want to move each of these guys back, but where in this, but the problem is you don't know exactly where they are supposed to lie, correct? This is what you want all of them, this is where you want all of them to lie in, but you have no idea of where they're supposed to be. So what we will do is first move all of them down to a standard point, the center, zero mean unit variance, and then find out what the best location for the entire lot is and shift the whole lot to this point. And this is our guess for the optimal location for all of these batches, right? Now, does the figure make sense to you? So now let's try to implement this, algorithmically. This is the process by which we do this is what is called batch normalization. It's a covariate adjustment that happens, and you can think of it as a covariate adjustment unit. So typically what we have is that you have the weighted sum of all of the inputs, and then you have an activation applied to it. I'm now going to stick a little yellow box between the weighted sum and the activation to adjust these values such that it accounts for this covariate shift. So batch norm can be thought of as a covariant adjustment unit that happens after the weighted addition of inputs and before the activation. And it's for simplification, to simplify computation, we're going to be doing this independently for every unit. And this adjustment actually occurs over individual mini batches, right? And here's how we will do it. So again, remember, we had an activation over there. You have the weighted sum z coming in, and then you have this covariate shift adjustment happening in the middle, which is a box, which is some computation box, but that in turn has two components to it. The first component is going to take the mini batch and shift it to the origin, as we saw in the figure. The second one is going to take the patch at the origin and move it to where you want it to be. Yes?
How do you know where you want it to be?
We're going to estimate that too, right? And so this is how we're going to move everything to the origin. For each mini batch, I can compute the mean of the mini batch and the standard deviation of the mini batch, and just a standard z norm. I subtract the mean, divide by the standard deviation component wise. What happens? The entire patch is now shifted to the origin, the mini batch, because we've subtracted the mean out. And because I've normalized them by standard deviation, in every direction now the standard deviation is 1, right? So I've taken the batch, shifted it to origin. After having shifted it to origin, now I will scale it up, because remember, I've normalized everything to have variance 1. Now I'm going to scale it up by some factor gamma, so that's bigger, and then shift it to some position beta. And gamma and beta are unknown. We're going to actually estimate this. You see what's happening over here, right? So here's how I can actually write the formula out. The mean for the mini batch is just the average of all of the z's coming in. The z is the weighted sum of inputs, right? You're going to have 1 z per training instance within the mini batch. So this is the average of all of those guys. I can also compute the standard deviation, which is just a z minus, the average of z minus mean of the mini batch whole squared, standard formula, right? And now, having done this, I can get the normalized, this is done over the entire mini batch. Once I estimate the mean and the variance, standard deviation, I can normalize each training instance within the mini batch by subtracting the mean and dividing by the standard deviation. Note that I'm adding an epsilon just to keep it stable, right? And now I can compute z hat by modifying the UI, scaling the UI by gamma and adding beta, right? So this is the overall operation that, yes?
So this is only used for the first layer, or can this be used for?
This logic applies to the entire network, right? So remember, this business of covariate shift is valid for every single parameter, for every single unit in your network. So this is going to apply for the entire network. Can, in principle, be applied to the entire network. So if you actually see this figure, Notice I've put a yellow box everywhere except for the final guy, right? Now, so here it is. There's a normalization to the 0 mean unit variance and then a shift to the correct position. Let me expand it out. The shift to the, I can write the whole thing like so. First there's the U, which normalizes everything to 0 mean unit variance. And then there's a second step which scales this guy up by gamma and adds a beta. So there are two parameters I've introduced into the process, the gamma and the beta. And I have to learn everything. So now let's look at gradient descent, how exactly this affects gradient descent. Now we of course know how standard gradient descent operates. We're going to be moving all the way back. We get the derivative of the divergence with respect to y. Then we can get the derivative of the divergence with respect to z hat. This is straightforward. This is just the standard thing. Then strange stuff happens over here. Okay, why does strange stuff happen? Just look at this guy. There are two parameters over here, which is beta and gamma. So remember, z hat is gamma times u plus beta, and and gamma and beta must be learned. So I need the derivative of the divergence with respect to beta and the derivative of the divergence with respect to gamma. And because z hat is simply gamma u plus beta, the derivative of the divergence with respect to beta is the same as the derivative of the divergence with respect to z hat. So this is easy, the first step. Similarly, the derivative with respect to gamma is also easy. So these are required to update gamma and beta. But then now you must propagate the derivative backwards to continue with backprop. And this is where things get tricky. What is the derivative with respect to u? That's easy from this formula. The derivative with respect to u is simply the derivative with respect to z hat times gamma. So far we are good, right? And now let me compute the derivative with respect to, there are multiple parameters over here. One is the standard deviation, the other is the mean. So, and the third is z. We want to compute the derivative of the divergence with respect to z. We've managed to get all the way down to u. How do you go from the derivative of the divergence with respect to u, from the derivative of the divergence with respect to u to the derivative of the with respect to z? So first, let's consider the derivative with respect to sigma squared. And we'll see why we must consider this. Now sigma squared is a sum, this term. So if you simply work out the standard derivative over here, you're going to find that the derivative with respect to sigma squared is the formula up there. Easy enough to work out, right? I can also compute now, observe that it has a summation, right? And here is the crazy bit. The sigma squared affects the divergence, but sigma squared affects the divergence by modifying every single input in the mini batch. So the derivative with respect to sigma squared is computed by by adding the influence of every single input in the mini batch, which explains the formula up there. You'll see that it's summing over the entire mini batch, right? Similarly, I can now compute the derivative with respect to the mean, straight from this formula again. And actually from this guy. I can compute the derivative with respect to the mean. I have the derivative with respect to u. So and again, I must add over all of the u's for the same reason, right? If I modify the mean, it modifies all of these u's which modify the divergence. So I have to add over all of the u's, right? And then finally, what is the derivative with respect to z? The derivative with respect to z has three components to it. First is the derivative with respect to the standard deviation. The second is the derivative with respect to the mean, and the third is the derivative with respect to directly with respect to z itself. So look at how z influences u. The value of z goes straight into u, right? So this is going to be simply the derivative. So this first, the upper term is the derivative with respect to u, scaled down by this guy. The value of z affects mu. So you have to also take the derivative with respect to mu. And the value of z also affects sigma squared. So you also have to take the derivative with respect to sigma squared. and all three of them must be added in order to compute the derivative of the divergence with respect to z. So this is kind of non-obvious and somewhat non-trivial to figure out. But once you begin drawing these little influence diagrams, you can see where the arithmetic actually comes out from. And thereafter, the rest of the backprop just continues. Right? So those of you who actually implemented batch norm might have encountered these formulae in the implementation. And some of it is actually hidden in PyTorch, I believe. But here's the arithmetic, right? So note that these are neuron specific, right? But then you've done all of this, but during test time, you're going to need a mu and a sigma to plug into this box. Where are the mu and sigma going to come from? You just average over all batches, and those are the values that you will retain. And gamma and beta, of course, have been estimated, right? Now, coming to your question, batch norm can be applied to some layers, to some neurons, all of this. At some point, the basic idea is what I have presented. It's supposed to normalize out covariate shift. Exactly where you want to apply it ends up becoming a heuristic. This is one of those many magic black boxes that training neural networks encounters all the time, right? But here is a typical result that has been reported by Yof and Szegedy when they first talked about it. The pluses, I think, are batch norm, is it? No, the solid blue line. And you can see that the classification performance converges rapidly to what you would get using standard training techniques in far fewer iterations, and you can actually end up with a better result. So this has the nice characteristic of not only speeding up training, but also arriving at a better result because you're accounting for covariate shifts. Now, one more thing, right? I have to draw in Trump everywhere. So I've explained several things based on this figure of this little figure I've showed, where you have some loss function, you've taken training samples, you're trying to fit the error over the training samples, and maybe it all works. The fact of the matter is you're never going to see something like this. Never, ever going to see something like this. What you're really going to see is, first, you have this risk that the network may just learn the values of the function at just these training instances. So you want to learn the dotted blue curve, you end up learning the red curve. This is not a good thing. But then here's a bigger problem, right? So let's say I'm working with MNIST. What is the dimensionality of MNIST? How many pixels? Yeah, that's 700 and something, right? I'm working in 700 dimensional space. And let's say each pixel has only 2 values. So how many possible input values am I looking at? 2 raised to 728, which is comparable to the size of the universe in atoms or something of that kind, right? Or maybe even larger. To completely specify the function, now all of these points lie on the corners of a hypercube. To completely specify the function, you must specify the value of the function at every single point on the corner of this hypercube, assuming that each pixel only takes 2 values, right? So now suppose I actually give you 100 trillion training examples or something equally absurd, which you're never going to observe, and I place all of these training examples on the corners of the hypercube where they are. Then if you randomly start off at some training example and just randomly choose a direction to travel in a spaceship with finite velocity, the universe will end before you hit the next training example if you're traveling only along the corners of the hypercube. That's how sparse your training data are. So if I work my way backwards, I'm getting the equivalent of just slightly more than 1 sample per dimension. And the real problem you're giving the neural network is this. Here's my spot, find me the function, right? This should even look reasonable. We don't stop to think about it. How much information am I actually providing the network? Not very much. In fact, nothing. And you're expecting it to perform magic. So you need additional constraints that will fill in the missing regions acceptably, right? Generalization. So a couple of things. Now let's go back and look at a simple binary classifier. Here we saw this example before. You have some x is the training value, y is the label, and you want the actual network output to follow the blue curve, right? If I make a large enough network, you can end up learning something like this. Is this what you want? Not really. What you want is the blue curve, right? Why does this happen? So why does this happen? All of these sharp changes over here happen because the perceptrons in the individual perceptrons in the network are capable of arbitrarily sharp changes, right? Arbitrarily steep. So each perceptron can rise almost vertically. Whereas if you decrease the weight in the perceptron, it's going to change much more slowly. So if you want to prevent the perceptron from learning this function, you want to ensure that the weights of the perceptron do not become too large, because if the weights in the perceptron become large, then it can become arbitrarily steep, right? And so the way we will do it is, first we are going to impose a constraint on the weight. We are going to say learn the perceptron, at the same time make sure that the weights are small. And how can we do this? Easily enough, I can just add, now here's the conventional training, the training loss. You're just taking the average divergence and you're trying to minimize the average divergence. To this guy, I will include a second term. I will say not only decrease the average divergence, also make sure that the weights of my units are small. And by ensuring that the weights of the unit are small, I'm enforcing smoothness. And I'm preventing it from learning that absurd function that you saw at each perceptron, right? So, and the importance of smoothness can be governed by this term lambda, which is your standard regularization term. Now, the other ways of doing this is just one example, right? So, how this affects learning is fairly straightforward. All that happens is that the gradient now has this additional lambda wk term, regardless of the technique that you actually use. And here's how it would go in. Now, there's a second way of imposing structure. The first one, of course, is that you can impose constraints on the weights by, say, making sure that the weights are small. But how about actually modifying the structure of the network itself? It turns out that the structure of the network also imposes constraints on the function that you learn. We know that MLPs are universal approximators. And so if I arbitrarily increase the size of the network, it can learn any odd wiggly function. And you don't want to learn wiggly functions. But then, for a given number of parameters, and this can actually be seen both empirically and to some extent can be shown on paper. For a given number of parameters, deeper networks impose more smoothness than shallow ones. Why is that? Each layer works on the outputs of the previous layer, which has already smoothed the input to some extent. So as you keep increasing the layers, you're working on smoother and smoother outputs. And so this necessarily enforces smoothness on what you learn. So here's an example. We have, in this example, we've seen this before. These are two different decision boundaries that we're trying to learn. In each case, we have 1,000 training examples. And we tried to learn a network with 660 units to learn this decision boundary using all the tricks of the trade, throw the kitchen sink at it. Here are the two results that we actually get. And they're not very good, right? 660 units in one flat layer. So, but then I take the same 660 units and rearrange them in different ways. So here there are 3 layers of 220 units, or 4 layers of 115, or 6 layers of 110, or 11 layers of 60 each. And what happens? The same number of units, but as the network gets deeper and deeper, you see that it's actually capturing the shape that I want to more and more. So this is again a standard property that you will observe, and it has to do with the fact that we are sort of imposing constraints on the function that the network will learn through its structure.
What is this picture meaning? This is a neural network of 11 layers?
This is not the network. This is the decision boundary it's trying to learn. But the network has 11 layers, right? Right. So we have training samples for these decision boundaries. Yes.
Is the total number of units in each of those examples the same?
660 exactly. Right. So that was the whole idea, right? I'm just taking the same number of units. I distribute them deep versus shallow, and you can see that going deep, actually gives you a greater smoothness and a better estimate of the loss function. Now, there are, what is the time here? Okay, we have a little time, 9 minutes, okay. So the last topic we will talk about is this so there are very many methods for regularizing networks that have been proposed. We just touched upon a couple of those. Batch norm, it's not really regularization, it's a covariate shift adjustment, turns out to be fairly effective. These other regularization terms through structure and through constraints on the parameters turn out to be very important in some problems. In other problems, they can actually come back and bite because you never know what you really need. So here are all the, eventually it descends to heuristics, right? But the last, but probably the most influential, technique in the past decade was this thing called dropout. Now, before we talk about dropout, you have to be familiar with this concept of bagging. How many of you have heard of bagging? If you haven't, when you train a classifier, this is an old technique going back to Leo Breiman in the 90s and the 80s. Turns out that instead of just suppose I give you a certain number of training samples. Instead of just training one classifier from the training samples, I could train many classifiers by drawing a random subset of the training data. And so I could train, I could use different learning algorithms, train classifier 1, classifier 2, classifier 3. And then when I get a test instance, I'm going to use all of these classifiers and vote over their decisions. And it turns out this will actually give you a much better result than just training a single classifier. So dropout purportedly just builds on this idea. Now consider a network of this kind, right? The network, when I give you a network of this kind, all I'm really doing is specifying architecture. I'm not telling you exactly what the parameters are. That's what must be learned. Now within this network, it turns out there are many hidden subnets. How is that? So here, for example, I got rid of a whole bunch of edges. Here's one subnet. I got rid of these guys, right? So depending on which bunch of edges I get rid of, I'm going to get a different network, right? So here's what I could do. I can train if the network has a total of n edges, how many different networks can I actually build from it? 2 raised to n. Each edge can be, may or may not be present, right? So I will try to simultaneously train all 2 raised to n networks. Of course, 2 raised to n is going to be very large for a large network. So rather than training all 2 raised to n networks independently, we will impose an extra constraint, which is to say that if I have these 2 networks, so let's say I have these 2 networks, something like this, and a different network which is, say, this guy. So these are the same number of neurons. One edge has changed, right? Observe that although they are different networks, they have similar structures. So I will impose a constraint that corresponding edges, if they are present in both networks, will have the same value. So you're going to have shared parameters. And with this one little constraint, the training process for learning the complete set of 2 raised to n possible networks becomes much simpler. So here's what I can do. For each training instance, I'm going to randomly select some subset of these edges and erase them, right? So here, for example, I have 3 different training instances. For each of the 3 training instances, I've chosen a different random subset of network edges and erase them. So what each of the 3 networks training instances is actually seeing is the network shown over here. The first guy sees this first network, the second one seeing the one to the right, in the middle, the third one is seeing the one to the end, right? So in effect, I'm going to get as many different networks as I have training instances. And if I keep changing the manner in which I select the edges to erase across iterations, eventually over many epochs, I'm going to see a great many different networks, all of which are being trained simultaneously, right? And so this is effectively what is really happening is that for a network with n neurons, we won't, so I misspoke. We don't actually switch off edges, we're switching off entire neurons, right? So for a network with n neurons, there are 2 raised to n possible subnets, and you can dropout is effectively sampling over all 2 raised to n possible subnets. There is a variant of this called drop connect, which actually eliminates edges. And the 2 are very similar in principle, right? And so, and then we are going to train the network, rest of the network exactly as before. Yes?
Doesn't this make the feature learning harder? Because in chessboard example, we thought that the neurons are interpreted as learning the edges.
Mm-hmm.
But if you keep dropping off the inputs randomly,
Mm-hmm.
it will be very harder to make them learn the feature.
If you have a network of exactly the optimal size, then yes, there isn't enough information. But typically what we do is our networks are much larger than what we need to actually learn the function.
But if you don't have, then in theory you can't.
Yeah, if the network is down to the minimum, you can't turn anything off, right? So I'll actually skip the actual algorithm for you, but the way in which it's implemented and the way the updates are performed are actually on the slide, so take a look. And this will, turn up in the quiz just to make sure that you've gone over this. And, we'll have 2 questions. So I'll skip the actual manner in which this is implemented. We're running out of time. But there's a couple of, there's one final issue that one must consider. So what we are really doing is we are trying to, the idea is that you have many classifiers. I have each classifier is looking at a different subset of the nodes, right? And this classifier is a function that operates on many different neurons. This is basically what we are doing. And what we would like to do is to get the average of the outputs of all of these classifiers simultaneously. So if you have 2 raised to n possible classifiers, what you really want to do is to run all 2 raised to n classifiers, compute the average output. And this we are going to approximate, and this is a very poor approximation, as the classifier, a single classifier of the expected value of sigma k xi, right? So you're moving the expectation into the function. This is not something that's mathematically correct, but turns out to be a pretty good approximation, which now says that for each neuron you can think of this. So what is the expected value over here? Remember, each neuron is being switched on or off by according to some probability, right? So the expected value is simply the value of the neuron multiplied by the probability of the neuron itself being switched off. And once you set it like so, then there are different ways of actually implementing this procedure, either by applying the weights to the alpha term to the weights, or scaling the activation itself down during training. Again, take a look at the slides, and if you have any questions, post on Piazza, right? So let me get to some typical results that Hinton reports, where they train, I think, I don't remember, this was an MNIST. They show that if you actually include dropout, the classification error falls tremendously compared to what you would get if you were not using dropout, right? And there are various variants on it, things like zone out, drop connect, where you drop individual edges, shake out, white out, you name it out. Once people realized that you can actually begin dropping things, then they came up with many variants. Other heuristics that you might have encountered, you don't actually let the training go all the way through. Sometimes you like to stop early by checking the performance on some held out set. Gradient clipping, yes?
Is dropout sometimes linked to overfitting? If network is getting more overfit, then it goes.
Bagging is intended to combat overfitting, in a sense, right? So yes. Another standard technique is if your gradients become too steep, it's likely that you actually overestimated them based on your current sample. So you clip them, And here's one technique that actually has been found to be very popular, which is to augment your training data. So for example, if you're trying to recognize Coca-Cola cans and somebody just gave you that one picture as your training instance, then you distort it in many which ways, and you come up with many instances of many synthetic training examples that you can also use to train your classifier. And this, it turns out, is one of the big things that you can do to actually improve your classifier, including for your homework if you have the time, right? So I'll stop over here. I think we're quite out of time. If you have any questions, post on Piazza. And in the next class, we will begin talking about convolutional neural networks, which we've already dealt with in the recitation. And the next homework is on CNNs. Thank you.